Hey, APChem peeps. So we're going to come back here to problem number 6. It says a buffer solution is prepared by containing a 0.5 molar NH3 and 0.2 molar NH4Cl. For ammonia NH3, the pKb is 4.75. Determine the pH of the solution. So ammonia, that's ammonia. And so when I'm looking at this problem, there's a couple things that I want to recognize first of all. They give us two solutions, but when I'm looking at this, they tell us that NH3 has a pKb. This is a weak acid, and this is one that I want to recognize. Or sorry, weak base. Ugh. It's a weak base. I want to recognize that as a weak base. It's a common weak base. So ammonia, yep, want to recognize that. They also give us this NH4Cl, and when I look at that, this NH4 kind of looks like NH3. This part is actually its conjugate. And the Cl part, what makes this part a little tricky is that, yeah, NH4 is part of the solubility rules, that Cl isn't part of the solubility rules. But because this is its conjugate, I'm going to keep this in my equation that I will write. But the Cl, that's a conjugate of a strong acid. And that I could take out because it's not going to reform with hydrogen. It's not going to react. So we're not worried about the Cl in this case. And so when I'm going on, or when we start this problem, we're doing the same thing that we do with all our other ones. We write a balanced net ionic equation. I am not dealing with a weak acid and a strong acid base. So I don't see any strong acids in here. This is the conjugate of it, so it's not actually the strong acid. So I don't have to do any stoichiometry. I could go about doing this with an ice table. We'll kind of show you a long way of doing this problem and then a short way of doing the problem. But here we go. We start off with our base. Because we're dealing with pKb, it might be nice to work with NH3, that's our base, and it's aqueous. And it reacts with water. So when we deal with weak acids, weak bases, we can react it with water. And because it's in equilibrium, we have the forward and reverse reaction yield signs. And we get NH4 plus. Because NH3 is a weak base, it will absorb a hydrogen from water, become NH4 plus. And that means if this was our base, this is our acid. The H2O gives off that H plus, becomes OH minus. And here's our conjugate acid. And here's our conjugate base. And so here's my equation. Now, determine the pH. Well, if I want pH, I need concentration of H plus, but they don't tell me concentration of H plus. But OH minus is here. If I can figure out the concentration of OH minus, then I can figure out the concentration of H plus because I know the relationship between things like pH and pOH. And so that's kind of the plan that we want to go about. But because we're in equilibrium, we have to start off with an ice table. And so in my ice table, I'm going to write out my initial conditions. Because they tell me molarity, I can put molarities in ice table. That's fine. I have 0.5 molar NH3. So 0.5 molar. I'm going to write in my ice table what this unit starts off as. It's molar, not moles. It's molar. And that's just going to be kind of a reminder to me here later. Then 0.20 molar NH4Cl, because this is, this will dissociate, and the Cl part I don't have to worry about. I can say that the 0.2 molar is the same for NH4 and for the Cl, and we don't have to worry about the Cl. So 0.20 molar NH4. The H2O liquid, we don't have to worry about. And the OH minus, we are not given any information about it. We can assume that this is just 0. And we don't have to have that. But then, with our change, because we don't have any OH minus, I'm going to need to, for this to be an equilibrium, there needs to be a shift over this way to produce more products. And then, so I know that I'm going to be subtracting X from this side and adding X on this side. And it'll just be like minus 1x because the coefficients is 1, plus 1x plus 1x because the coefficients are 1. When I get my equilibrium value, it's going to be 0.5 minus x, and 0.2 minus x, and x. Now that I have that, I can actually put into my equilibrium expression. But, oh no, they don't give us the equilibrium expression. I got to figure that out. But remember that when we do this, it's not Ka that we are writing, because for Ka, you have to have H plus over here. It has to be for an acid equation. This is a Kb equation because we have OH minus. That also goes along with what they gave us, which is kind of nice because they gave us a pKb. We'll get that part here in a bit. Okay? So we need the Kb expression and the Kb value. But I know Kb, it's equal to concentration of NH3 and OH minus. Oh, sorry, NH4 plus, concentration of OH minus over concentration of NH3. So products over reactants. The other part is I do need this Kb value, or sorry, they gave me the pKb. Just kind of like how pH works. We know pKb, it's equal to the negative log of Kb. But to get that Kb, I need to do 10 to the negative pKb. So it's equal to 10 to the negative 4.75. If I do that, I end up with 1.78 times 10 to the negative fifth. All right, now I'm ready to use that value in my equilibrium expression. It's 1.78 times 10 to the negative fifth is equal to, now I'm putting this stuff in. I have 0.2, I should have 0 in here, minus x times x over 0.5 minus x. Now here's where, again, it gets a little tricky. When I see things in my equilibrium expression like minus x, plus x, those things make my life really hard, especially with doing the math. And I'm going to end up having like x squared and x and other places. But because my Kb value here is 10 to the negative fifth, it's smaller than 10 to the negative fourth, I can probably take out these minus x's. And so it works, and we want to recognize that. It makes our life a lot easier. And so now I need to solve for this x. To do that, I can multiply this by 0.5 and divide by 0.2 to solve for the x. And I get x equals 0.1234444, and or 4.44 times 10 to the negative fifth. And so that's my x value. But oh no, I did not actually answer my question yet because I solved for x. I need to determine the pH, but this x, that is equal to the OH minus concentration. If I can figure out POH, the pH and the POH, they have to add up to 14. So POH is equal to negative log of the concentration of OH minus. So I have negative log of 4.44 times 10 to the negative fifth. I get that POH is equal to 4.35. Yeah. And so I know that the pH plus 4.35 have to add up to 14 so that I can figure out my pH is actually equal to 9.65. Oofda. And checking my sig figs, I have P's. Oh yeah, so I have two sig figs here. I have two sig figs in this thing. Yeah, I'm gonna have two sig figs. Remember, for pH and pOH, all that kind of stuff, sig figs are counted after the decimal. It is just so weird, but that is just kind of how it works. So when we work through these problems, this is the long way of going about doing it. And we did this ice table, figured out the concentration of the OH minus and plugged it in for pOH, all that kind of stuff. That's cool. But some things just to keep in mind about this is does make sense because we have a weak base that our pH is coming out to be basic. And our pOH is also coming out to be basic because it's a low pOH. It's lower than 7, and that's how the pOH scale works. But pH scale, that's kind of more common than what we use. And so that part makes sense. So that's one way of doing it. Second way of doing it is an easier way. And so I'll show you that. It starts off with this beginning part for the ice table. But there's something about it that I don't have to do all this other work in order to do it. And if I recognize something that they told us right here at the very beginning, it's going to make my life a lot easier. And they told us that we had a buffer solution, you guys. This is a buffer. We have the base and its conjugate. There's really nothing else here to begin with. And so it is just a buffer. Awesome. And if we have a buffer, that means that we can use Henderson-Hasselbalch. And where that equation pH equals pKa plus the log of the concentration of A minus over HA. When we see A minus and HA, this really is just talking about the conjugate pair. This part has to be talking about the base. This part has to be talking about the acid. So we need to know which one's which. This is the acid. That's the base. And so we, to get the pH, we need the pKa. But oh no, they gave us the pKb. But something really cool about it is just like how pH and pOH add up to 14, the same thing works with pKa, because pKa is like the acid, and then pKb is like the base part. They also add up to 14. So if I know that this is 4.75, I can figure out what the pKa is. And so the pKa is equal to 4.75 minus this, we get 9.25. And so I have, all right. So now that I have my pKa, I can start putting that into my Henderson-Hasselbalch equation. I have my 9.25 for my pKa plus the log, and it has to be for the base and its concentrations. So I have concentrations. That's in molar. Awesome. And so for the base, this is my base. It's the 0.50 divided by the acid. This was my conjugate acid, and it's 0.20. Remember, in Henderson-Hasselbalch, these things are conjugate pairs. So you're not talking about like a weak acid with a strong base or anything like that. You're not talking about this and OH. You're not talking about this acid and OH. You're talking about the conjugate pair. And then when we end up doing the math, we divide these numbers. You take the log of it, plus 9.25, and you end up with 9.65, the same answer that we came up with before. Nice. But this was just kind of like a shorter route. So if you recognize a buffer and you're just dealing with the conjugate pairs, that's awesome. You just have to do Henderson-Hasselbalch. If you're given a strong acid, strong base, you'll see in the next problem how to deal with that, and then you can deal with Henderson.